two speakers today. So our speakers will be Ítalo, the CTO at Lykon, and Sat, who's an engineering manager at SolarisBank. Both incredibly experienced and both successful tech professionals. So on to you, Ítalo, if you'd like to kick us off first of all.
Yeah, so my name is Ítalo and I work as a CTO at Lykon. Lykon is a medtech kind of company here in Berlin. Previously, before Lykon, I worked in N26 here in Berlin as an engineer manager. And previously from that, I worked at HelloFresh, also here in Berlin. And then I joined Lykon basically with the point to actually scale up the team and dive a little bit more into the med tech kind of area. Today, I'd like to talk about designing for failure and what that means exactly for us software developers and SRE and DevOps, everybody in the DevOps culture. So designing for failure, it's a topic that I like to talk a lot about, especially because when you work in a distributed system, you have so many possibilities of things going wrong and things actually failing that you have to know exactly how to handle this kind of failures and which kind of strategies and patterns you can adopt on your software today to actually avoid those failures. How do we design systems for the unexpected, right? Like how can we design systems that are ready for fail? Today, I'd like to go through starting with what is resilience and how do we apply concepts of resilient software into our day-to-day work. We're going to go through latency control, isolation, self-healing, traffic control, observability, and in the end, service meshes. And hopefully, you're going to get something good out of this talk, something that you can use tomorrow or starting on a working day. So before we dive too much into the technical topics, I'd like you to think about a plane. Think about an airplane, right? Well, now that we have Corona, it's much more complicated. But last year, we had 39 million flights going on across the year throughout the world, right? That's a lot of flights if you think about it. It's a huge number. There's so many people involved. There's so much logistics involved in the whole aviation field. And 39 million flights, actually, it's a lot. And unfortunately, out of those numbers, we had 23 deadly crashes. And out of those, 28 big fatalities there. Only one crash was actually, reported from the FAA in the US, which was regarded to be a software failure. Even though it's a tragedy, it's a single flight that actually went down because of a software failure. But definitely there were many more software failures during this whole aviation problem going on. So if you're aware from last year, the 737 MAX case, that was the one. There were 2 flights. Basically, software fails all the time, including airplanes, including, like now with the SpaceX going to the space. For sure, software fails all the time. But airplanes, they were built with something called ELMS. So it's this picture there kind of thing. There's a system called ELMS, which is electrical load management system. And that software was designed in the 90s, basically to make sure airplanes can be more reliable with their electrical systems. So just as an example, in a 737, you can find about 7 batteries across the airplane, right? So if one goes down, it falls back to the next one, and the next one, and next one, and so on and so forth, until we reach the 7th. Even then, if the 7th battery actually goes down, for whatever reason, there is a mechanical fan that goes down of the airplane, and then it starts rotating with the wind pressure and the wind speed, and it generates mechanical energy, so it keeps the essentials running in the airplane. So that is the whole secret of this electrical load management system. There are many different specifications for that, but the idea was created in the 90s by Boeing, basically. And think about your systems today. Think about your software today. Can they run only keeping the essentials of your systems, all the external dependencies that it's not needed for your software to actually run? Can it run like that? So that is what I want to talk about today. I like this quote quite a lot. Resilience is a requirement, not a feature, from Liang Wu. So lots of time in my experience when I was, discussing with product people, especially, or, business analysts and so on, we never talked about resilience, right? Like maybe because the industries that I was currently in didn't really care much about it. But that was a flaw, right? Like we always have to care about resilience, and it should be a first-class citizen. Like we should care about how our software is going to fail so we can prevent that it fails, or at least have some sort of failovers. Yeah, and that's basically what Liang Guo tried to actually pass here in this quote. So let's start with latency control. That's the first step. I have many examples here, and most of them are in Go, but most of them can be applied to any kind of language that you have or that you use, because they are abstract kind of concepts. So latency control. We start with timeouts, and timeouts are tricky, right? So we have client timeouts, we have server timeouts, we have many different options of creating timeouts in our application. So the idea is that you actually map out all your external dependencies. So a timeout can be applied to, in this case, I'm calling just this HTTP stat library here, which is, website, which is gonna apply like some sort of delay, so I can actually simulate failure. But timeouts also can be applied to your databases and should be applied to database connections, or through any kind of Kafka connections that you have as a producer, so on and so forth. So in Go, at least, it's easy to set a timeout. You can just create simple timeout in your client, in your HTTP client. You set your timeout, you create a request, and you execute the request. Simple result. This one will fail because the the website is going to reply in 300 milliseconds and 3000 milliseconds. And I'm saying that here, we're gonna time out in 2 seconds. So this is a simple timeout in Go and how we create it. You can be a little bit more specific. And I believe this is the same for every language. My background is more C# kind of oriented, and then coming into Go, passing through PHP as well. And all of that was possible. So essentially you can go really deep and you can say, okay, I want to set a timeout for my client. I want to set the transport layer timeouts where I want to control the dialer and say, okay, timeout on the dial calls after 30 seconds, or keep alive after 30 seconds. You can even go to the TLS handshake and so on and so forth. If you use TCP connections, you can also do the same on layer 4. So you can actually just set your timeouts for TCP connections. Client timeouts are super versatile and super important for us to have if you want to avoid a cascading failure, right? If you don't set those timeouts on your client, if your third-party dependency starts failing, then you're actually going to have a failure on your software, which is going to eventually, replicate your customers. Avoiding cascading failure, this is a super easy one to actually add, is client timeouts. Here's another way of doing this in Go with contexts. In Go, we have this new context with timeout that can be applied on the request. It's a little bit different than the previous one, like this one that I showed here with 2 seconds timeout. The reason being, when you use a context like this and you have multiple requests using the same context, if one request fails, it's going to cancel the other request automatically, which is great, even if you're doing parallel requests. So you have a little bit more control and you can actually propagate that timeout callback whenever it fails. So client timeouts, super versatile, super useful. Of course, you also have the server timeouts. If we're building an HTTP server in this case, or a gRPC server, or whatever you're into, you can set some timeouts as well. So here as an example, we have read timeouts, we have write timeouts. Those ones are probably the most important ones when creating an HTTP server. You can also use idle timeouts for idle connections. You can, read the header timeout, which is one of the first things is going to happen whenever a connection comes in. And setting these timeouts, and these numbers are completely arbitrary. I just put it there as an example. Guessing those numbers is the really hard thing to do. You're going to need a lot of monitoring to figure out those numbers. But essentially, Nginx has a pretty good standard of those numbers, so I just copy them here. So jumping next from timeouts to circuit breakers. And circuit breaking, it's something, again, it's another concept that came from electrical industry, actually. Probably all of you have a circuit breaker in your home, and those are actually built to avoid any kind of, putting your house into fire if there is circuit happening. So if there is a failure, circuit breakers are there to make sure it stops sending requests to a third party. So let's take this example right here. I have Google as my external dependency, right? And I'm just doing a call to Google, so a normal HTTP call, very simple. And I just see here, if Google returns anything bigger than, bigger or equals status bad request, which is for 100, I will return an error and I'm going to trip the circuit. So right here on the top, we just use a library called Go Breaker. If I'm not mistaken, it's from Sony. And in Go, that's basically how we do it. And then you have you have this ready to trip function that you can, that is going to be called every time a circuit trips. And it trips when you return an error, essentially on the call, right? And it's going to trip up to a point, right? You want to open your circuit whenever it reaches a specific rule that you set. In this case, I'm setting a rule for if it fails more than 3 times and the failure ratio is bigger than 0.6, I actually want to open the circuit. And whenever the circuit is open, no request is going to be sent to Google anymore, which is great if you want to give some breathe to your external dependency, right? You want to make sure it can recover properly and you're not bombarding the external dependency with more calls. And then you can handle that in a better way. So circuit breakers were introduced, if anybody here is from the Java world, you probably heard about Hystrix. And Hystrix was a pattern. It's an old pattern, but it was introduced mainly by Netflix a while ago. Now it's deprecated because we're moving, technology changes and we're moving more towards sidecar kind of proxies and this kind of things instead of, this fat clients that do a lot of things. But Hystrix was one of those, and it was very well designed. It had many different things for, to help resilience overall. I think now in Java you have resilience for J, which is also a good framework. But Hystrix gave you this nice dashboard where you could easily actually see which circuits were being bombarded with requests, like this one right here on the top. And then you could see which ones were open or closed, right? Whenever they are open, you could trigger an alert and your team could actually investigate what was happening. So definitely something super cool that Hystrix put it into the industry. In Go, there is an implementation as well of Hystrix, which is fairly solid. But as I said, many people are moving more to sidecar proxy instead of pattern, instead of the big clients. So we're moving ahead from that. But again, circuit breakers are nothing by itself, right? They're going to open the circuit, great. They're going to avoid a bombarding kind of thing into your third-party dependency, or whatever dependency you have, could be your database as well. So it's going to avoid that. But how do you make sure it can, it can go back to the normal state, which is a closed circuit? So for that, you can apply many different things to that. One of them are the retries. And retry mechanisms are very useful if you don't want to, if you don't want to be constantly going manually into your service and fixing problems that might be happening. So in this sequence diagram, very simple here, I have a consumer service, which is my service, and I have a producer service, which is Google in this case, right? From the example before. So I have this consumer service. It calls, it's going to call the producer service, and we're going to wrap it around a circuit breaker. Later on, we're going to wrap it around a retrier, and the retrier is a possibility for us to configure rules for our calls, for external calls, to retry. Simple, right? But a lot of these we just forget whenever we develop, an external call to an API. So doing this in Go, again, super easy. We can use this avast. You can build it yourself, of course, or you can use this avast library, which is super good, where you specify a retry callback, and this is going to wrap it around. It's going to be wrapped around a circuit breaker. So you have a retry do, and internally, again, we're going to call an external URL, and we're going to read the body here just as an example. But what is the real thing here that is important to notice is this retry attempts. And this retry attempts, I'm going to retry 3 times before I actually trip a circuit breaker. So I retry 3 times and then I trip. And then circuit breaker will then trip 3 times as well. So we have 6 times in total. And then finally it's going to fail. So we also have a retry delay type because you don't want to retry one call after the other. Like that's not really very effective. So you want to do probably something called exponential backoff, which essentially like calls an API, and if it doesn't work, or an external service, if it doesn't work, it's going to give some time and then retry again. And if it doesn't work, it exponentially grows that time until the last retry or the last attempt that you set. So basically, this is the retry mechanism, and it's super useful, especially when mapping out your external dependencies to wrap it around this. So next, we jump into isolation. And one of the patterns from isolation that I like to talk about is called bulkheads. Again, something that was implemented in the Netflix Hystrix kind of implementation, but bulkheads actually came from the naval industry. So I believe most of you already watched Titanic. The Titanic actually set sail, I think, in 1912, if I'm not mistaken, and unfortunately sank in the middle of the Atlantic. So the reason why, if you watch the movie, you're going to see that as well. But if you read any papers about the Titanic and why it went down, there was a design failure in the whole system, right? So this GIF here kind of, reproduces what was the design failure. So the Titanic hit the iceberg, and it had many different bulkheads. So this yellow lines, I hope you guys can see it. These yellow lines here represent a bulkhead. And the point of a bulkhead is actually to contain something, right? Either water, fire, or anything that basically could be harmful to the structure of the ship in this case. In the design itself, because the Titanic hit in 4 points of the bulkhead in the iceberg, the water starts flowing into the ship. There was this design failure in the bulkhead. So the bulkheads are supposed to contain the water, but above, like on the top of the ceiling of the bulkhead, there was a material that they were using where the water actually could go through. So it went through up the bulkhead to the next bulkhead to the next bulkhead until the 4th, and then the ship was too heavy to actually hold that weight, and then it broke in the middle and then it sank. So again, the principles of bulkhead here can be replicated into software. And that's what Netflix did, actually. So when building Hystrix, and you can still see, it's still open source, so you can still see how they implemented this. The concept is that you have a thread pool, right? So you have a thread pool to call your external dependencies. So think about Google again. So you're going to call the Google API, and you have a thread pool of, 10 threads, let's say. And let's say that one of them gets, it hangs because Google is slow to reply or whatever. Maybe Google is a bad example, but whatever other dependency that you have. And if that hangs, it's going to hang only a single thread instead of your whole application, right? So because you're managing them through a thread pool. So that is the concept of bulkhead. You isolate the failure in a single place where the other ones can still work. And that's the whole point of bulkheads. So most people implement that with thread pools. In C# is the same thing. In Go, we use, the Go sync pool, which is the Go routines, because we don't have threads per se, we have Go routines. So essentially, that's what you want to avoid. And you can apply this to any external call, or also any external job that you're doing, right? Like you're doing a heavy job in different threads, and you don't want to hang your application. Obviously, threads are the way to go, but then you have to sync them, and you have to make sure you manage them properly, and you distribute them across the workload. So that is the whole point of bulkheads. And this concept came from the naval industry. Next, we talk about self-healing. And self-healing applications are super important if you don't want to be awakened on the night and have to fix everything by yourself. So this example here, especially if you're into Kubernetes or some sort of container orchestration, you always start with health checks. This can be applied to any health check system like Nginx or HA Proxy or Kube, if you use it. This one is specifically for Kube, and all we want to do is actually map out our dependencies. This is probably the most important thing, is figuring out your external dependencies and how important they are for your application to work. In this case right here, I'm mapping out a database, mapping out a payment service, for example, and again, Google. And then I also have a liveness check, which is, as I said, specifically for Kubernetes here, where I'm going to just say, okay, if I have 100 Go routines going on in my runtime, then that's bad. Then we should flag it to Kubernetes to restart our pod. So basically, when you do this health checks, you normally get this simple standard way of, reporting failure into your system. If everything is okay, you're normally going to have this URL right here that you can reach, and you're going to get this okay right here. And also for the ready endpoint, you're also going to get those okays. But otherwise, if something fails, you can get a little detail right here of what's happening. But the important thing is this, is the status code. So the status code is going to be reported to your, in the case of Kubernetes, to the scheduler that's actually going to check it out, what's happening. And then it's going to schedule a new pod to come up and bring you your pod that is failing down. Same is going to be applied if you go to Nginx, for instance, where it uses outlier host detection based on status codes from your health checks to actually either take you out of the load balancing algorithm or to replace your machine with a new one. So your instance with a new one. Doesn't matter if it's a pod or if it's AMI that you're going to put there, whatever it is, it's going to try to replace it as long as you have the whole automation going on. So if you use Kube, that's kind of given for you. It's automatic as long as you configure this. So health checks, super important. If you don't have it in your applications today, you should definitely have it. Okay, then again, self-healing, we can talk about Outboxer. And the Outboxer pattern is something, at least people that comes from ops don't deal much with it. But if you come from software engineering itself and software development, you probably face these issues. So the Outboxer, imagine that you have a dependency. Imagine that you have a event-driven architecture going on, right? So you have either Kafka or RabbitMQ as your message broker. So Kafka would be an example here. I'm doing AMQP, which is RabbitMQ protocol. And let's say that you are a producer of messages, right? So you're producing a lot of messages, and unfortunately, you can't send them anymore because RabbitMQ cluster is down. The whole cluster is down. It's not highly available, so it went down. How do you handle those messages? Imagine that you're doing a checkout and you do that, like you don't do that synchronously, so you're going to do asynchronously. And now Rabbit is not there. What do? Do you fail the whole transaction? Do you reply to your customer saying, sorry, we have a problem with our transaction? Or do you still try to process that and then process that account later, so that transaction later? So that is the whole point of the Outboxer. So normally you open a connection to your main storage. So in this case, it's Postgres. And you also open a connection to your message broker. And here I'm just wrapping around Postgres into this Postgres wrapper, which we're going to show here. So we do these Outboxer, and we define the data store, we define the event stream, and finally we define a check interval. So every second or every whatever interval you put here, we're going to check if there are any new messages in our primary store. And if there is any message, if there are any messages, we're going to try to send it to whatever event stream you have. If the event stream is not available, no problem. We're going to process later on. That is the whole point of the Outboxer, right? Is that we save this in the primary storage instead of our event storage. Now, if Kafka is your primary storage, then you might want to rethink this. Probably not useful to use the Outboxer pattern. But essentially here, you're just saying you have a standard way of sending messages throughout your application. So you have a single interface or API that you can use. And internally, it will handle all of the failure over for you. If it's not there, it's going to save on your primary storage. And once it's back up, you don't need to worry because it's going to send all the messages to your to your event stream. Now, if you use your primary storage should probably be highly available. Otherwise, it's pointless. It's not going to work. So again, I think there is something like this for C#. I left a link in the end of this presentation, so For Java, I don't know. Maybe someone in the audience here knows. It would be nice to know. In Go, I created this, this little library here called the Outboxer. So if anybody is curious, checking out how it's implemented and or want to contribute, I'll be happy to accept contributions. Moving forward to traffic control. And on traffic control, simple rule, rate limiters, right? Like we start with rate limiting. Probably most of you are aware of how rate limiters work. In Go, we have this example, Ulule limiter, which is a cool library. And the most basic rate limiting rule you can start with is in-memory rate limiting, which is you have a single instance of your app and you defined how often you want to rate limit your requests. In this case, it's 2 requests per minute. And I will define my storage. Here is an in-memory storage. And I can attach some middlewares for, for HTTP if I use HTTP. But essentially, this will bring a problem. If you have multiple instances, then you have different counters on every single instance. And if you're load balancing them without a sticky algorithm, then you might have an inconsistency on how your counters will be. For that, we go to distributed rate limiters. And then, of course, you're going to introduce another dependency, which is an external distributed storage. But in this case, you're going to get requests in through your load balancer, which will load balance across different instances. And then you're going to count them synchronously into your distributed storage. Normally, it has to be very highly available if you're doing this. And then you can actually be sure that the counters are going to be the same across instances whenever you need them. And many libraries support this. In that library specifically, you can just create this floor of the API remains as before. So it just works. The same can be applied in C#. There's a similar thing. Cool. So nothing I talked about up to now is useful. You don't have observability. You have to figure out all those numbers, all those strategies that you want to use. And without observability, nothing really is going to work. So metrics are the first step, right? You want to make sure you have some metrics to rely on. And metrics, again, when you are in a distributed environment or when you are in a microservice environment, if you have a heterogeneous one with multiple different languages across your whole stack, it might be tricky to actually standardize metrics. So I tend to use something called OSIS, which is a standard that I mainly use for metrics and distributed tracing. But it's to standardize across languages, right? So they have clients for of the major languages that we have today, and report the metrics the same way, which is great for building like, this generic dashboards or whatever kind of metrics and alerts you want to have out of it. In this case here, I'm just simple example of Prometheus and how we can report metrics with open census. Same is valid for distributed tracing. So we have distributed tracing right here with open census. And what I like about open census and open tracing in this case, this is open census, this is open tracing, is that they're joining forces this year with open telemetry. And open telemetry is already on the beta version, which is great. And hopefully they will release it still this year, the final version. And they're basically joining those two things into a single API that can be used with different backends. So you can report metrics to, let's say, to Datadog or to Honeycomb, or you can report it to Prometheus. Distributed tracing is the same. You can report it to X-Ray or StackTrace or Jaeger in that case. So all with the same code throughout your app. So that's why I like open telemetry. It's really good. That's a lot of things. A lot of patterns, and I didn't even scratch the surface of different patterns that you can actually have in a distributed system. But those are a lot of things, right? Like we're talking about when you have like a single service, that's okay to implement those things. When you have 10 services, maybe it's okay to implement all of those patterns if you want to be resilient. But when you have like 100 services or 1,000 services, it starts to become almost impossible to actually control how you want to apply those rules into all those services. And if you have multiple languages, then it's another level of complexity. That's when service mesh actually went into play. And I'm not here to say if service mesh is good or bad. I know there's a lot of discussion into that. Just saying something that was created with the intent of actually resolving problems with our distributed systems. So example here, service mesh with Istio and Kubernetes, right? The ones that I have most experience with. Service mesh, Istio architecture, very simple. It has an Envoy proxy running aside your aside your container, and it has a control plane, right? And this control plane is going to control all the certificate issuing or rules, authentication, authorization rules, so on and so forth. So a few examples of how we can do those things that I explained before only with service meshes is, let's start with the timeouts. This is super simple. We create a virtual service, which is a service in Kubernetes that is going to run kind of in front of your actual Kubernetes service, where then you can set the timeout for the request. So every request that is coming into your service, it's going to time out under this 10 seconds in this case, right? We can also have retries, obviously. You can say, okay, every request that is trying to call me right now, it's going to retry every 3 times. You can have every 2 seconds delay between the retries. You can have different strategies here as well. And you can have secret breakers as well. So if you define a destination rule to where you're calling something, you can say, okay, this is going to be wrapped around a secret breaker, and we're also going to have outlier detection. So we can, remove out of the load balancing algorithm in case something happens. So secret breakers are also cool. There's a lot of different examples in the Istio documentation. There is something called Istio by example, which is even better, with actual examples on how you can apply distributed systems standards or patterns with Istio, which is super cool. And also you get visualization of your mesh out of the box, right? So you use something like visual your way in exact each workload you have breakers, anything else. So just to recap, we talked about resilience and how that can be applied into our workday. We saw standards from the naval industry, the aviation industry, and the electrical engineering industries that we apply in software, but we barely knew where these standards actually came from. We talked about latency control, timeout, circuit breakers, and retries. We talked about isolation and bulkhead standards, like how can we protect our resources with bulkheads. We talk about self-healing applications, so health checks and outboxer patterns, traffic control with rate limiters, observability, and service meshes. So there's a lot more to talk about into this, but since I probably already reached my time, and also there's so much to talk in different talks, I left some resources. Whoops, there we go. You can reach me out here. You see my talk in GitHub if you like. This coffee shop application here, I love coffee. And Coffee Shop is an application that is highly available and reliable with the standards that I described here. It's written in Go, so I hope you're comfortable with that. Here is a cool documentation from Microsoft with a lot of resilience patterns that can be applied into your software. They're pretty generic. The examples are with C#, but obviously you can do it with any language. Super cool documentation, very well written. If you want to reach me out on Twitter, please feel free to follow me there, and I'm happy to answer any questions. And I really appreciate your time today here, and thank you very much.
So yeah, as I say, thanks Ítalo. Sat, if you're ready, I'm sure everyone's looking forward to it.
Hi everybody. Usually it's more comfortable when you're talking to a crowd and you can look at the faces, you can look at the reactions, see if you're boring or not, right? So this is going to be an interesting challenge. Nevertheless, what I wanted to do was take some of your time to talk about something that we did in solarisBank, where I'm from. We wanted to talk about you build it, you run it, the whole philosophy that's been going on for a couple of years right now. I started looking at the current state of blogs and videos on this topic, and then realized that there was quite a lot of articles written about it. And you know what? There's even 2 talks by tech banks like Monzo and some other bank which did some similar talk. So I thought about it like, what would I be able to do different, right? You could possibly go on to YouTube and look at these talks or read something from an article. So I started thinking about it with my team, and we figured out that we'll share our experience as quick as possible and open up a discussion to you so that you'd be able to ask us a lot of questions about the implementation or about the challenges that we had. So basically, I'm Satyajit Ranjeev. That's usually a mouthful for a lot of people. So a lot of them call me Sat or Satya. With me are two engineers from solarisBank who were very, let's say, who were the key roles who set up this whole you build it, you run it process, Flavio and Lakshman. Both of them, along with me, hopefully will be able to answer a lot of questions. So wide ranges from organizational challenges to all the way to technical challenges that we've faced. For those of you who haven't heard about solarisBank, we happen to be a tech company with a banking license. So what does that mean? It actually means that we power a lot of fintechs in Germany. Companies like Penta, Contest, Tomorrow, and very recently a company called Vivid Money. Basically, a lot of the banks that, the new banks that's running use solarisBank's APIs. We're a B2B company that provides banking as a service. Or in engineering jargon, we provide APIs that allow tech companies to do easy banking stuff without all of the German regulations or the European regulations. So I work in the teams that actually build the core infrastructure of the company. When I say infrastructure here, I mean the services that work on financial protocol level. We communicate with the SEPA world or the SWIFT networks. And if you're not familiar with that, that basically means like we move money from one bank to another and we keep track of your balances. For a long time, we used a third-party provider to do these things. As we evolved as a company, we understood that it would be very beneficial for us to build and maintain our own core infrastructure, our own core banking infrastructure. When people started talking about the core banking systems, they were thinking, oh yeah, we want it to be highly available. We want it to be a consistent system, and we want it to be partition tolerant. And if you are familiar with the CAP theorem, you'll see that you'll start scoffing at this idea. So we had to make some trade-off. And if you've watched this movie called Catch Me If You Can, you remember that Leonardo DiCaprio was basically forging a lot of checks and moving from places to places, right? Eventually, the bank caught on. And this is something that we did as well, right? But we are an eventually consistent system, though we are able to catch up a lot more quicker than the ones in the movie. We built a microservices-based architecture. We have quite a lot of services. We're on AWS. And as mentioned, the eventual consistency is built out of an event-based system. There's actually a wonderful talk done quite early on by one of our engineers, Armin, which I've linked the YouTube video over here as well. So you might want to go and look at it if you want to understand a little more in depth on how we built this architecture. The previous talk was very interesting because it was talking about building fault-tolerant systems and highly available systems. And this is exactly something that we want to do, right? And we want, if you ask anybody, it'll be very nice to have a 100% available system. Like when you think about it, you want your banks to actually have a 100% available system. Whenever you're doing a transaction, you want the transaction to actually work. But in reality, you'll come close to a fraction of 99.99 or 99.49s and things like that. So what we realize is that if we wanted to go this extra mile, I mean, there's a lot of things that we could do with code, with a lot of good architecture principles. But at one point of time, we need to be able to maintain it as well. The further we are away from maintaining the systems that we are building, the further we are away from actually getting a feedback cycle of what works and what doesn't work. And if you look at just a communication, a communication link between when you have few people And when you have multiple people, you can see that the communication channel goes all crisscross and haywire. And this is what exactly happens when you try to have different teams work with different roles. So somewhere, I'm not sure when exactly Werner Vogels gave this interview to ACMQ, but one of the interviews, he basically coined this term, you build it, you run it. He was talking about how Amazon started running their own systems, or basically the developers were encouraged, or there was no operations teams. Right? Basically, if you wrote the code, you were responsible to run and maintain it. Now, this is not very surprising if you're a very small company. I've worked with small and large companies. I've been in companies where I was the very first engineer, and at that point of time, we would basically write our code and deploy it and run it. And as company sizes increases, you see that you have different roles, like people who are into development, people who are into testing, into quality assurance and support and so on. And people find out fancy names as well for it. But what you lose is basically the feedback loop that's essential for improving the quality of the service. And this was one of the primary reasons that we chose to run our own system. So you can see one of an interesting quote, which a Netflix SRE manager said, right? When things are broken, you want people with the best context trying to fix it. And when these people try to fix this, a lot of lessons is learned doing that. And this talk is basically about this journey of us going into maintaining our own services. The early time when we started building our services, we had a traditional operations team which maintained these services. Since we are a regulated company, we have a lot of requirements on who gets access to production environments, who gets access to our database and to logs. Every time we had to make changes on the way that we deployed, or if we wanted to make some changes on the infrastructure, there was a lot of communication involved in the operation team. And the feedback cycle for understanding what worked was way too long. And the very first step that we started taking up was taking more ownership of the things that were being deployed. We started migrating all of our services from an account that was owned by the operations team to an account that was owned by my teams itself. And I know this is, mentioned a lot over here, especially with DevOps meetups and in a lot of SRE talks. But we started everything with code. Deployments, so we use Kubernetes, basically EKS, so our deployments, the roles that we have, access controls that we have, almost everything possible, we actually put it either through Terraform or through Git. I mean, Terraform and Git, so that we would have a paper trail for a lot of our regulators. And also it helped us to be reversible. So when something goes wrong, it was easier to roll back into a state that we knew that worked. And it was very important that we actually work with a mindset that everything is code. The next thing that we started working on was we started thinking about, okay, how do we know that something is going wrong? Now, it's great when you know that something is crashed, like all of your requests are failing, or people are not able to use the API. I mean, you don't need an alerting mechanism. Most likely, your customers will start calling you or start complaining on Twitter, so you'll invariably know about it, right? The best thing is when you're able to understand the situation even before something like that happens. For example, 60% of your requests are failing, or there's a high utilization of the database. So we started working on understanding how our system was performing, and we started setting up metrics. We started instrumenting how long does a request take, or how much of utilization of our infrastructure was normal, which was not normal. And we started creating alerts based on this. We use Prometheus for a lot of our metrics. We use a little bit of CloudWatch as well. And Prometheus has this alert manager, which we were able to actually use to send alerts to Slack channels. And this was a very good way to start off with. Whenever we knew the system was, something wrong was starting to happen with the system, we got a notification on Slack. Getting a notification on Slack is just the beginning, right? You need to understand, okay, fine, I've got this alert, I've got something is happening over here, and now I need to figure out, okay, is this something that needs to be dealt with right now? Is this a disruption or a degradation to the service? And if it is so, then that is an incident. We need to deal with it, sometimes immediately, sometimes it could wait a little bit longer. And for this, we actually started setting up an incident response team. And the incident response team basically consists of a few roles which would jump into it whenever an alert was raised or whenever somebody noticed of an incident. So every week, what we would do is we set up a first responder. Now, her role was to keep an eye on the alerts channel and set up an incident response team if it was necessary. On the trigger of the alert, the first responder starts to identify the severity of the alert. Is this something that is bringing the entire bank down, or is it something that is it is becoming a challenge? There are a few services that are being affected, but not necessarily the entire thing. Or maybe it is something trivial that can be snoozed off and dealt with later on. Now, if it was an incident with a severity level of something around 4, we have different levels. The first responder identifies it as an incident and starts dealing with it. So she creates a Slack channel and appoints an incident commander. An incident commander is a person who sets up communications and logistics for the team. He or she delegates roles and takes up complete responsibility for the decision when a consensus couldn't be taken on how to proceed. The main focus on the incident commander is to ensure that the incident is mitigated and the operation of business is back to normal. The first responder also picks up a few engineers who actually assesses the current impact of the incident, analyzes the symptoms and what are the side effects that could be caused from this. And also, after a decision is made on how to proceed, apply the mitigation. Now, usually, there's also a communication lead along with this in this team. Now, the communication lead sometimes happens to be the incident commander when we are not able to find anybody else. What the communication lead does is post regular updates on the statuses of the service in public channels, make sure that all of our stakeholders knows about the impacts, starts logging all of the actions, all of the decisions and the clues that we have in Slack or in other places. Now, she's also responsible to shield a lot of the interferences from outside teams. Now, it was interesting that with our experience, we had volunteers for almost every incident. There's somebody who actually volunteered to be the incident commander, somebody who volunteered to be the engineers, and we were able to mitigate the incident. Now, mitigating the incident, I think it's a lot on the mindset, and the idea is to actually focus on the incident and try to restore the service as soon as possible. It's not trying to go and try to find out why this is not working. It is more to make sure that we get back. So the simplest thing would be to roll back to a version that was working, right? Or to roll back to a backup that we already had. Once the incident was mitigated, we usually set up a postmortem. Here we review the incident in detail to see exactly what went wrong. This is where we go into the root cause analysis. We understand why it went wrong, and we make sure we also figure out what we can do to make sure that it doesn't happen again. We usually schedule a postmortem within 3 to 5 days since the incident. We prepare a page with a timeline of all of the events that occurred. And now you can actually see that the communications lead, when he or she was writing down what the events that occurred, that helps a lot in the postmortem part of it. The timeline, hopefully includes all of the important changes in status and the impact, and also some key action taken by some responders. In this meeting, we look at what went well, what went wrong, and where we got lucky. We gather what are the next steps that we could do. Like probably it was a bug and hopefully we can fix it. So create a ticket in the engineering board, or maybe we needed better alerts. Maybe we needed to instrument better metrics so that we were able to capture this way ahead of time, or in general, improve the whole process by itself. Now, we had the luxury of having a operations team in the beginning. So we did most of this during office hours. This was quite good enough when we started. And for a lot of teams, I think, coming up to this itself is a big step, and this is more than enough. But we were one of the most critical teams in solarisBank. We were building services that needed to be highly available. And we took the next step, which was to make sure that we would go 24/7 on call. Now, when things are getting serious, when it is actually affecting your sleep, right? And we needed to be very critical on how we deal with this. One of the most important things that we did was to make sure that we keep health and sanity of the engineer on call as our first priority. Going on call needed a lot of groundwork. Apart from laws and regulations in Germany, there was to generally keep the sanity in the team, right? Usually, a lot of people are reluctant of going 24/7 because it has been either misused or could become a source of worry. And what we did was we made it sure that this was not mandatory. I think this was one of the first things that we did, that we made sure that it was a voluntary basis to help the engineers to make the decision. Being on call was a venue for all of us in the team to understand the limitations of our system and eventually to improve it. Being closer to why something failed was helping us to understand that we could build better services. We started looking into industry standard for on-call rotation. The on-call frequency, we figured out that shouldn't be too short. No, it should be too long. Too short, and then you have people burning, and you're talking about burnouts. And too long, generally people forget about how things actually worked. So we figured out that the sweet spot would have been about 6 weeks. And so we took 1 engineer per week. Interestingly enough, since we made it optional, we found that we actually got more than 6 engineers who were willing to be on call. We realized that working out of business hours is actually a sacrifice that engineers are making. You're sacrificing your personal time, and we value it and respect the work-life balance. So if you wanted somebody to work beyond business time, we wanted to make sure that we compensate enough. There have been different ways different companies have dealt with how we compensate. We decided a fixed amount for the week that you're on call would be the best. Because we've actually heard some stories where a fairly popular company provided an instant-based compensation. So there was an engineer who basically had more incidents when he was on call, so that he could get some money for his holiday. Ideally, you don't want your services to break during on call, or you don't want to be woken up in the middle of the night. And so basically, think of it as free money that you should be getting. Hopefully the incident happens during work hours, and then you're able to solve it, and there are a lot more of people looking at it. Now, once we had the alerting mechanism, all of the necessary things that was set, we needed a mechanism to get paged if at all something happened in the middle of the night. Now, Slack messages, usually don't help you when you're sleeping soundly at 2 a.m. So we set up PagerDuty to handle all of the alerting and paging. Basically, we set it up based on different criticality levels. I also mentioned a while before how we set up criticality levels. Now, whenever the criticality level is high enough above a threshold, then PagerDuty basically calls, first notifies and then calls the on-call engineer. We also know that we have to be mindful that everybody has their personal needs. Maybe somebody is in the shower or in the loo, and we give a time to react, so that you're able to have your own personal life, but jump into when you need to react on an incident. But sometimes, we are all human, and we probably don't listen to the call that's coming in, or you're too asleep and too exhausted that we snooze off the phone call. And this time we also have built a method to escalate. So all of the escalation basically goes to the manager, which happens to be me here. And then if I don't pick it up, it goes to my manager, and eventually it goes to the CTO. And so this is the escalation method that we had. And actually, interestingly, when we started that, we were joking up that, it's only happened very few times. And recently we had the whole cycle of escalation where it went to the manager, then it went to the VP, and went to the CTO, and then came back to the rest of the team. So, things happen. The next thing was when basically you did get paged and something went wrong, right? The most important thing that we realized that we help our engineers was to make sure that they don't try to investigate, like Mr. Sherlock over here, right? In the middle of the night, the best thing that you can do is to follow a standard procedure, right? Either to roll back the services or to toggle a feature flag that was activated or increase the capacity. So we provided runbooks. So every alert basically has a runbook which tells the engineer what to do if the alert is triggered. So a set of instructions or operations that the on-call engineer can perform when paged so as to restore the service. At the middle of the night, it's best not to panic. One of my favorite books, by the way. If you haven't read it, I would recommend doing so. The Hitchhiker's Guide to the Galaxy. So basically not to panic and not to go into a root cause analysis mode. Basically just try to bring the service back and running. Hopefully the incident is mitigated in the middle of the night and you need to have some rest. And this is also something we tackled. Of course, being in Germany, a lot of rules and regulations are there to ensure that employees' health is taken care of. So usually there needs to be 11-hour resting period after somebody's woken up in the middle of the night. So we started tackling that. We tried out a couple of methods by having a fallback schedules or a fallback roster when somebody is not available. We even tried out a little bit of tweaking of how we would react this. But it was very, very critical that if somebody was woken up in the night, that you would have a bit of a rest before starting up the next shift. The final thing that we actually worked out was how to hand over the on-call once you have completed your on-call shift. And we brought up a checklist of things that happened during the on-call and what the next engineer basically needs to figure out. I just looked at my time and I realized that I have been speaking for 25 minutes, and that's quite a lot, right? So over this process, we built our own services, and we've managed to run and maintain our own services. It's quite a lot of things that I've actually spoken over here. I've spoken about incident management. I've spoken about how you need to make everything as code, or make your infrastructure as code, which is very key to being able to maintain the services that you have built. You also have to have a lot of alerting and metrics to also see that, to also notify that your services are probably going to crash even before they do crash. And a lot of laws and regulations that goes into ensuring that the engineers who are on call have a fairly decent time when they are working with an incident. The first and foremost thing, I think, is the mindset that we all need to adapt, which is basically that to understand that running or maintaining the systems that we've built actually provides a lot more of value than letting somebody else build it. Thank you very much for listening to my long-winded chat.
I have a question for Seb. I wonder what, from your experience, is kind of the boundary conditions for actually making this rebuild it, rerun it work. because in my experience, so I work in a company where we have hundreds of microservices, many databases, and lots of engineers only work in small parts of the actual website. And if we were to enact something like we build it, we run it, I fear that we would have like 60 people on call or something, and that would just be crazy. So I wonder, like to get a bit more of how your infrastructure actually looks like. So how big is everything, and are the specific teams handling their own stuff, or is it really that people from one part of the application take care of everything over the weekend?
Yeah, I could definitely see that, right? Thanks for the question. So if I've understood you correct, right, it is like when you have so many services and so many teams working on it, do you basically have one team which is responsible, or you spread it across these different? At least in my case and in my team's case, it's actually very specific. So we're working on the very low infrastructure of the company, and these are specific, let's say, products that the rest of the company uses, and we only maintain the services that we have built. And what we are planning to do in solarisBank basically is to actually take these lessons that we've learned and push it into all the rest of the company. So basically we have different teams, like we have teams working on cards, we have teams working on accounts and things like that. So we want to enable that these teams start becoming on call as well. Not on call, but at least move into the direction of you build it, you run it. So if you remember in the beginning of the talk, I was talking about how we didn't set up on call at all first, but rather, be able to maintain our own systems during office hours, right? And this is something that you can probably start off with as well, where different teams, they have a narrow scope, right? Some people work on parts of the website, or some people work on parts of the other system. So being able to create your own alerts when you know that something is crashing or something is not working, and that specific team gets, let's say, not woken up, but notified that, hey, something is wrong, and then they set up an incident response team and work on it. That would be a nice way to go, right? We're also thinking about how do we figure out this budget, and how do we make sure that we can spread it across the entire company. And yes, I know we are thinking of even having 60 engineers, or 50 engineers being on call at some point of time.
Thank you very much, Ítalo and Sat. That was great.